Hey guys, so in this video I'm going to introduce the idea of angular momentum, which is the kind of momentum that you have if you have rotation. Let's check it out. So remember, if you have linear speed is v, you're going to have linear momentum. Now we used to call this just momentum because we only had one type, but now that we're going to have two types, we have to make a distinction between them. So linear momentum is good old little p, and it's just mass times velocity. So the units are kilograms for mass and meters per second for velocity. So you just multiply an object's mass and its velocity, and that's its momentum. If you have rotational speed, that's w, that's omega. You have angular momentum or rotational momentum, and it's going to take the letter L instead, right? So instead of p, it's L. Now instead of m, you're going to use the angular equivalent of mass, which is I. Hopefully you get that. And the angular equivalent of v, which is omega. So you can think of this equation as like perfectly translating into angular, into rotational variables, okay? The units are going to be a little bit different. It's going to be kilograms per meter times meters squared divided by seconds, okay? And that's because of the makeup of the equation, okay? So I, moment of inertia, is made up of, let's say the moment of inertia of a point mass is mr squared, but this works for all of them. Mass is kilograms times meter squared, okay? And that's I. Omega is radians per second. So if I combine these two, okay, sorry, I meant to write this over here. Omega is in radians per second. If I combine these two, you end up with kilograms times meters squared times radians per second. But a radian, you might have seen when I talked about the fact that a radian is really a meter over a meter. So it's a ratio of 2 meters. So what we do is from this here, we just get rid of the radian because we can think of it as the meters canceling out. And you're left with kilograms meter squared over second. So that's how this comes about. So the units are different for these two guys, okay? So another difference between them is that linear momentum is absolute. If your mass is 10, your mass is 10. It doesn't matter. If your velocity is 10, it's always 10 unless it, as long as it doesn't change. And then you just multiply those two. However, angular momentum is relative. And what that means is that it depends on the axis of rotation, just like torque. So if you remember torque, if you push a door here with a force of 10, you get a different torque than if you push here. Same thing with angular momentum. You could have the same object spinning at the same speed, but if it's spinning at a different distance from the center, it's going to have a different momentum. Okay? So momentum depends on the axis of rotation, changes with the axis of rotation, which is something that doesn't happen with linear momentum. Last point I want to make here is not to confuse angular momentum, which is what we just talked about, and it's L equals I omega, with moments of inertia. Okay, so even though you have angular momentum, it's not the same as moment of inertia. These are two different things. In fact, moment of inertia is part of the momentum equation. It's this guy right here, I. Okay, so got these similar terms. Moment of inertia obviously is I, which is the angular equivalent of mass. Okay, so don't confuse those two. Let's do a quick example and show you how to calculate angular momentum for an object. So I have a solid cylinder. This tells me I'm supposed to use the moments of inertia equation of I equals half mr squared. It says here that the mass is 5 and the radius is 2. So if you want, you can actually calculate this. I equals half, mass is 5, 2 squared. So this is going to be the moment of inertia of 10. It says it rotates about a perpendicular axis through its center with 120 RPM. So here's a solid cylinder, okay? An axis through the center of a solid cylinder. This is a disc, but imagine this was a long cylinder. An axis that's perpendicular to it is just an axis through the cylinder like this. Perpendicular, so 90 degrees at the face of the cylinder, and it rotates about its center, which means it just does this, right? Cylinder just rotates around itself, and the equation for that, when you have a rotation like this, is is this right here. Okay? So it's rotating with an RPM of 120. I want to know what is the angular momentum about its central axis. So basically, what is L? Well, L is I omega. I know I, we just got that, it's 10, but we don't have omega. But you know, hopefully by now, you're tired of doing this, you know that you can convert RPM into omega. Omega is 2 pi f, and then frequency can change into RPM. So frequency is RPM over 60, so I can replace this with RPM over 60. Okay, so it's going to be 2 pi 120 over 60, so it's going to be 4 pi. Okay, so I'm going to put 4 pi here, which means L is going to be 40 pi, which is 126 kilograms meter squared seconds. All right, very straightforward. Just plug it into the equation. The only thing we have to do is convert RPM into omega. That's it for this one. Hoping this makes sense. Let me know if you have any questions, and let's keep going.